Hi, it's time for another math easy solution. Turn to discuss further into partial fraction decomposition, and now look at the proof for basically the simplest case of partial fraction decomposition. Basically, in my earlier videos on partial fraction decomposition, I went over the techniques in decomposing rational functions, but I did not explain why those techniques worked. So basically in this video I will go over a proof of the simplest case for partial fraction decomposition, and some examples of these fractions are shown below, such as this one, x squared plus 1 divided by x minus 1 times x plus 2, and then there's an x minus 3. As you can see, the denominator here will have eventually an x3 at the bottom, and then the top's x2. So this is a proper function. So this is proper fraction, and this one here on the right side is x plus 7 is x minus 5, x plus 2, and again that is an x versus an x squared, because you're eventually going to multiply these x squared. So these are all proper functions right here, or fractions, and you can learn more about these proper and improper in my earlier videos. So now in proving this simplest case, we first have to write this down to account for all of these, let's say, variations of x squared plus 1, x plus 7, etc. So the simplest case is basically having to show that we have to split up this right here. Let's say n over x, which is a polynomial, and on the bottom is x minus a1 times it by, well, x minus a2, and then you keep doing this, times it by, all the way to x minus, we'll call it a d right here. So this keeps going on, and now we have to prove that this could be split up into partial fractions, a1 over x minus a1 right here, plus, and then we'll have an a2 as another coefficient, x minus a2 plus, etc. Keep going on and on until we get, well, a d over x minus a d right here. Yeah, and now these ai's right here, or these a coefficients, these are all different. They're all unique, so there's no repeating factors, such as in this case if we had a squared, then that would be repeating, and that's not what we'll cover in this example or in this proof right here. And also n of x is a polynomial of degree at most d minus 1, so it's always a proper fraction. So what this means, if it's d minus 1, so as you can see, if this is up to d, these multiply together. So if you were to multiply here, you would have an x d at the bottom, so the polynomial at the top has to be at most d minus 1. So this becomes, well, proper. So this is exactly like I showed over here. We had an x squared over x cubed, x over x squared. So this is the most it can be, but it doesn't have to be d minus 1. Yeah, so basically now in proving that the above theorem holds true, we first need to show that the following theorem holds true first. So we'll call this lemma 1, or just lemma. In another video I'll go over lemma 2. Basically, note that lemma is just a word. It means that it's a subsidiary theorem or a secondary theorem which will help in the overall proof. So let n of x and d of x be polynomials of degree n and d, where basically n is less than or equal to d. So it's at most is degree d. And now if we suppose that a is not a 0 of d of x, so what this means is basically d of a is not equal to 0, then there is a polynomial p of x of degree p, which is again less than d, and a number a, such that we get, and I'll explain this all in a bit, n of x over d of x times it by x minus a equals 2, and now we have a of x right here, an a over x minus a, so a partial fraction like this, plus p of x over d of x. Yeah, so what we're doing over here is basically saying, well, if a is not a 0 of d of x, so in this case right here we can't, if we have d of a, we can't have a 0 because we already have this part here. So we're trying to get a non-repeating factor right there. And the idea in all of this is simply to look at this whole thing, which has many different factors, and separate all of them, all of them except this x minus a, and then writing everything else as one function. So if we could prove this case, if we had these all as one function, then we could just keep repeating this lemma 1, and I'll get to that in a bit. And also then this is p of x is degree p, which is less than d. So this is a proper fraction right there. Yeah, so once again, now we have to just prove lemma 1, and then we can apply it repeatedly to prove the overall partial fraction decomposition theorem for the simplest case. So as I go through this, it will start to become just makes more sense in what I'm trying to do here. So proof of lemma 1, what we could do is we could take this right side and then just multiply it out by the common denominator. So what we could do is write, well, n over x, and there's a dxa, x minus a equals to a over x minus a plus p over x d of x. And now we just multiply this top and bottom by, well, x minus a, just so we can add these up. X minus, and now this one here we multiply by d of x, and then this is here at the bottom, d of x. So now our common denominator is going to be x minus a times d of x right here. So when we do that and equate it, so this would just become, well, a over a times d of x plus p of x times x minus a, all divided by x minus a d of x. So as you can see, when we multiply this out, we get this this over here, and this equals to, well, on this left side, n of x divided by dx over x minus a. So those are the exact same denominators here. So this means that the top part, n of x, has to equal to a times d of x, so just the numerators of both of the equate, or just multiply. We can just multiply this out, these cancel, etc. So we get now p of x times x minus a. So what this means now is if we let x equals a, or at x equals to a, let's go at x equals to a right here, what we will get is n of a is equal to a times d of a, and the reason we're doing this is so that this goes to 0. So this would be a minus a, that goes to 0. So now we have an n of a and a d of a, and none of these are 0, or this one's not a 0. So this right here can't equal 0, so we could solve, and now a is equal to n of a divided by d of a. So we've proven that a has a value in this, so now we just have to solve for, well, p of x. So what we could do is write p of x on its own. So we have p of x like this, move this p of x times by x minus a. Here this equals 2 just by shifting this to the left side. So we have n of x minus a times d of x right here. Yeah, so now from what we know is that this n of x right here, if we scroll up in the lemma, we know that n of x has a degree of n, which is at most d, and d of x has a degree of d right here. So what this means is has a degree of at most d, and now this one right here has a degree of d, has a degree of exactly d, and these are just polynomials. Degree of exactly d right here. So what this means is p of x times x minus a, this whole thing has a degree of d, and that's this right here. Because if we just add these two together, since we're adding, we're not multiplying, the degree stays as the highest one, which is d. So this has a degree of d, of exactly d right here, of d. But now if we were to solve p of x by itself, we would get, well, a p of x equals 2, well, n of x minus d of x over x, then we're dividing by x minus a right here. So the overall function this basically would need to be a degree of d minus 1. So p of x has to have a degree, it has to have a degree of d minus 1, because we're going to be eventually dividing by an x. It has to have a degree of d minus 1. So if this is true, then we've proven lemma 1. So if this case is true, and also a is and then we also get an a right here. So what we've just shown is that we've shown these two values that can exist to make the lemma true. Yeah, so basically we've just proved lemma 1, because that's all we were trying to do, was find p of x and a. So right here we found there's a polynomial p of x of p less than d, and a number a such that this whole thing holds true, and we were able to find a, which equals to n of a divided by d of a, and p of x is a polynomial, has to be a degree of d minus 1, which is less than d. Yeah, and now we can basically apply lemma 1 repeatedly to prove the overall theorem. So in the first step, let's let d of x equals 2. Right here, this will be equal to x minus, we'll go x minus a2 times by, x minus a3 times, and it keeps going on and on until we have an x minus a d right here. And we let a equals to a1 right here. So what we have over here, this d of x now has a degree now of, d minus 1. That's because we've removed the x minus a1. So now this is just as multiply x d times minus 1, so d minus 1 times. So now what we get is, by applying lemma 1, we have n of x over now a d of x, which equals to this whole thing right there. So this would be x minus a2 times, it keeps going on and on, x minus a d, now multiplied by x minus a1 right here, where this is our d of x. Now this equals 2. By applying lemma 1, we get a1 over x minus a1 plus, now this is the p of x, which has a degree which is less than d minus 1. So p of x, and now this equals 2. Yeah, the denominator is just d of x, which is this x minus a2 times by, keeps going on and on, x minus a d right here. Yeah, and now basically the degree of p of x right here, p of x has a degree of, at most, which is going to be d minus 2, has a degree, at most, which is going to be d minus 2, because the degree of d in this case is, d minus 1. This is d minus 1 degree, so this has to be, less than d minus 1, so at most d minus 2. Also, just go back here, just this one here has to have a degree of, at most, d minus 1. I just wanted to clarify that, and that's because this degree has at most d, and this has a degree of d. So if this had a degree of d, you could eventually subtract 2x to the power of d powers, and they would basically subtract, and you'll have a smaller degree. So this p of x, could be just any power less than d. And now what we do is, as you can see, we could just apply this same case again. So we could take this thing and bring it down here, and now we could apply lemma 1 again. Lemma 1 again. So when we do that, in this case we let, now our new d of x is going to be, let d of x equal to, equals to now x minus a3, and then times all the way until x minus a d. And what we get is, and then we also had, let's say, let a equals to a2. So we keep doing this, and then we get, we get p of x on the tops equal to, divided by x minus a, this is going to be a3, times all the way until x minus a d, and now we have an x minus a2. Applying lemma 1, this equals to a2 over x minus a2 plus, now what we get is a q of x. And q of x, and this is going to be, well, this is, because remember, this is our new d of x. Actually, up to here is a new d of x. So we get x minus a3 times it by all the way till x minus a d right here. So we get all this, and we put these together, we get, so far, we get n of x, and now we have, yeah, what we have, well, before I get to this, I just want to say, now this, this q of x has a degree of, at most, this is going to be at most, and it's going to be, because this one here is a degree of d minus 2 degree, so this is always going to be less a degree d minus 3. So degrees just keep getting smaller and smaller. And now this, what we'll get is, well, this is x minus a1 times it by x minus a2, etc., all the way to x minus a d. This equals, so far, a1 over x minus a1 plus a2 over x minus a2 plus, and now we have this q of x over x minus a3 times it all the way, x minus a d. So this is basically what we have, and this bottom is just written differently from here. This is the same thing, as move this to the left, and we get exactly what we were dealing with. So now if you keep repeating this, so keep repeating lemma 1, what we'll eventually get, yeah, what we will eventually get if we keep repeating this is basically our final answer, which would be, well, n of x over x minus a1 times it by all the way here x minus a d equals to a1 over x minus a1 plus, and it keeps going on and on until we get the last part, ad over x minus a d right here. Yeah, and as you can see here, this is exactly our initial theorem. So this is the proof for it, but just a special note is that when you get near the end, notice how there's no there is no q of x or polynomial there. That's because this degree here is degree 1, so this degree has to be degree 0, which is also a coefficient. Yeah, so if we were to write this down, at the last two terms, we get, let's say we had a y of x right here, divided by a x minus a d minus 1, so that's the second last term. Now we have an x a d right here. So in this case, let's let this this is the last term, d of x, that'll be our d of x function to apply the lemma. This one, in this case, will have a equals to a d minus 1. So now if we apply lemma 1, we get, well, a d minus 1, and now we get a x minus a d minus 1 right here. Now we have to add, this becomes a polynomial z of x, divided by, in this last term, d of x, which is going to be x minus a d right here. So as you can see, this degree is degree 1. There's just a power of 1 there. So if this is degree 1, this has to be degree, well, minus this one. It's always just one less at most. So this has to be degree 0. Exactly like how this is degree d minus 3, this is, no, I mean d minus 2, so you see this is d minus 2, this has to be d minus 3. If this is degree d minus 1, this p of x has to be degree d minus 2. So it's always one less at max. So if this is degree 0, what this means is, well, this is just a coefficient. For example, any number, let's say 3, that's a degree of 0, that's also a degree of 0. So this is just a coefficient. So what this means is this just equals 2a d minus 1 x minus a d minus 1 plus, and now we could just add a coefficient, and we'll call this a of d, x minus a d. So that's what these last two terms, you can solve it. That's why there's no polynomial inside here when we apply the lemma, because it goes to basically a coefficient. And anyways, that is all for today. Hopefully you follow through this pretty extensive example. In a later video, I'll go over the general case, which includes repeating factors, and later we'll also see nonlinear factors. Anyways, that's all for today. Hopefully you learned from this pretty extensive proof video. Yeah, and like always, you can download these exact notes in the link below, and stay tuned for another math